How can this work at impossible scale? May 1930. Manhattan's bedrock trembles under pneumatic hammers. The Empire State Building's foundation crews blast through 25 feet of Manhattan schist, carving out 55,000 cubic yards of rock and earth. Steam shovels claw at limestone deposits laid down 400 million years ago. The clock starts ticking on America's most ambitious construction deadline. The steel arrives by railroad from Pittsburgh Mills, where Bethlehem Steel's foundries run around the clock. Each beam gets fabricated to exact specifications, with steam-powered machines drilling rivet holes through 3-inch thick steel plates. Every beam carries chalk markings indicating its precise position in the 86-story puzzle above. Column sections weigh up to 4 tons each, requiring specialized railroad cars with reinforced wheel trucks. Horizontal girders span 60 feet without intermediate support, their web patterns designed to flex under wind loads without breaking. The steel framework alone demands 60,000 tons of precisely engineered components, each piece numbered and tracked through the supply chain. 4 separate railroad lines deliver materials to staging areas scattered across Manhattan's grid. Trucks haul steel beams through narrow city streets at dawn, before traffic clogs the arteries. Their drivers navigate turns so tight that beams sometimes overhang sidewalks by 15 feet. Derrick operators position the massive Otis Fensom construction hoists, each capable of lifting 15 tons to heights exceeding 400 feet. These steam-powered giants burn 3 tons of coal per day, their boiler smoke adding to Manhattan's industrial haze. The scheduling requires military precision that would make a railroad dispatcher proud. A single delayed shipment can idle 300 workers for an entire shift, costing the project $2,000 in lost wages. At ground level, rivet gangs assemble their portable forges like medieval blacksmiths preparing for battle. Each 4-man crew operates with surgical efficiency born from years of skyscraper construction. The heater tends a coal forge that reaches 2,000 degrees Fahrenheit, hot enough to melt copper. Red-hot rivets glow like molten bullets fresh from the fire. The tosser hurls rivets 40 feet through the air to the catcher, who snares them in a metal funnel while dodging wind gusts that could knock a man off his perch. The bucker up holds the rivet steady with a heavy iron bar, while the gunman drives it home with a pneumatic hammer delivering 800 blows per minute. Each rivet must be driven within 30 seconds of leaving the forge, or it cools too much to form a proper seal. The sound is absolutely deafening. Pneumatic hammers rattle at 120 decibels, loud enough to damage hearing permanently. Steel rings against steel in metallic thunder that echoes between Manhattan's canyon walls like cannon fire. Workers communicate through hand signals and shouted commands, barely audible above the industrial symphony. Each rivet must cool and shrink to create an unbreakable bond stronger than the steel itself. A poorly driven rivet means structural failure 40 stories above the street, potentially killing dozens of pedestrians below. Speed becomes absolute obsession. General contractor John Starrett implements assembly line techniques borrowed directly from Henry Ford's automobile plants in Detroit. Teams specialize in specific tasks, with steel erection crews completing 4.5 stories per week. The building rises at a rate of 1 floor every 2.5 days, faster than any structure in history. By September, the framework reaches the 20th floor, its skeleton visible from Brooklyn. Photographers capture workers eating lunch on steel beams suspended 400 feet above Fifth Avenue, their legs dangling over the void with casual indifference to death. Floor decking follows immediately behind the steel crews like a concrete wave. Workers pour concrete onto corrugated steel forms, creating composite floors that distribute loads across the entire structure. Each floor requires 200 cubic yards of concrete mixed on-site in rotating drum mixers powered by steam engines. The concrete contains Portland cement, sand, and gravel aggregate sized to specific tolerances measured in fractions of inches. Steam-powered hoists lift concrete buckets weighing 2 tons each to working levels in continuous cycles, their cables stretching under the enormous loads. The limestone cladding operation begins while upper floors are still rising into the clouds. Indiana limestone arrives pre-cut from quarries in Bedford, each piece shaped by Italian stonecutters using techniques unchanged since the Renaissance. Individual stone blocks weigh between 500 and 3,000 pounds, requiring specialized rigging to prevent cracking during transport. Derrick operators position stones with millimeter precision, using steel cables and wooden guides, sometimes taking an hour to place a single piece. Masons secure each block with bronze anchors and lead-sealed joints that expand and contract with temperature changes. The limestone facade requires 37,000 individual stones, each numbered and positioned according to architectural drawings that cover an entire warehouse floor. Elevator shaft construction presents unique engineering challenges that push technology to its limits. The building requires 73 elevators traveling at speeds up to 700 feet per minute, fast enough to make passengers' ears pop from pressure changes. Otis Elevator Company installs guide rails with tolerances measured in thousandths of an inch, straighter than a rifle barrel over distances exceeding 1,000 feet. Steel cables woven from hundreds of individual wires must support passenger loads while maintaining perfect vertical alignment. Safety mechanisms include spring-loaded brakes that engage automatically if cables fail, though the thought of plummeting 40 floors haunts every rider. Interior mechanical systems advance simultaneously on multiple floors. Electrical contractors install 43 miles of wiring through steel conduits embedded in concrete floors, enough wire to stretch from Manhattan to Philadelphia. The building requires its own electrical substation capable of generating 40,000 kilowatts, more power than many small cities. Plumbing crews lay 70 miles of water pipes and waste lines, creating a circulatory system that must function reliably at altitudes where water pressure becomes problematic. Steam heating systems distribute warmth through radiators positioned in over 6,000 individual offices, each requiring precise pressure regulation. Supply logistics become increasingly complex as the building rises toward the clouds. Material hoists operate continuously 16 hours per day, lifting everything from limestone blocks to office furniture in an endless mechanical ballet. Scheduling coordinators track thousands of components moving through the construction pipeline using charts that cover entire walls. A single bottleneck in steel delivery or concrete mixing can cascade through multiple trades, costing thousands of dollars in lost productivity per hour. Weather adds unpredictable variables that no amount of planning can eliminate. Winter winds at 400 feet exceed 60 miles per hour, strong enough to blow a man off his feet, forcing work stoppages during severe storms. Steel becomes treacherous when coated with ice, turning every step into a potential death trap. Workers wear leather gloves with metal studs for better grip on frozen steel beams that can shatter fingers like glass. Temperature variations cause steel to expand and contract by inches, affecting the precision fits required for rivet installation and sometimes forcing crews to reheat and reshape components. The topping out ceremony occurs on September 9, 1930, just 13 months after groundbreaking. The final steel beam, painted white and signed by hundreds of workers, rises to the 102nd floor amid cheers that echo through Manhattan streets. At 1,350 feet above street level, the Empire State Building claims the title of world's tallest structure, surpassing the Chrysler Building by 200 feet. The mooring mast for dirigibles adds another 200 feet of height, though no airship ever successfully docks in Manhattan's turbulent wind patterns that make navigation impossible. Final construction phases focus on interior finishing that transforms raw space into offices. Marble crews install lobby walls using rose-colored marble from quarries in Tennessee and Georgia, each slab weighing up to 800 pounds. The lobby ceiling reaches 3 stories high, supported by steel trusses hidden behind decorative panels that create the illusion of floating stone. Brass fixtures, custom manufactured in Connecticut foundries, weigh over 40 tons combined and require teams of 6 men to install safely. The building opens 13 months and 20 days after groundbreaking, setting a construction speed record that stands unbroken. Total construction cost reaches $41 million, equivalent to $700 million in modern currency. The structure contains 67,000 tons of steel, 10 million bricks, and enough electrical wire to circle Manhattan Island 14 times. But what invisible engineering decisions made such unprecedented speed possible when modern skyscrapers often require 5 years to complete?